12. Chapter 12, we're going to continue talking about probability, but in a different kind of way. So what we're going to be doing in chapter 12 is talking about something called a probability distribution. So it's basically what we're going to be doing is creating a function that outputs probabilities and talk about kind of how to do that. Is everybody okay at least on with that notion initially? Let's go and see how it goes. So we're going to start by defining something called a random variable. That is a quantity whose value depends on chance. It's basically a variable in a probability sense. So if we're talking about the probability situation that we're trying to model is like rolling 2 die, the probability variable there would be like the outcome, the possible outcome for your roll, right? Like you roll a 2, a 3, a 4, a 5, a 6, 7, 8, 9, 10, 11, or 12. So X would represent one of those possible rolls. Is everybody okay with that idea? A discrete random variable is the probability that only takes on a finite or countable number of possible values, like our dice rolling example we just gave, right? There's only, 10 possible outcomes, 2 through 12, or 11 possible outcomes, I forget now. Whatever. You guys get the idea though, right? And you can also have a continuous random variable. So that's a variable that can take on any value within some interval. So if we were, say we were measuring the heights of students, and we wanted to find out the probability the student was at least, like 2 meters tall. Well, height is a continuous variable, right? You could be 2 meters tall, you could be 2.1 meters tall, you could be 2.01 meters tall, you could be 2.001 meters tall. Like that's a continuous random variable, right? Is everybody okay with that idea? And we'll look at distributions in this chapter that are both continuous and discrete. And the behavior is a little bit different on those. So typically we let random variables be represented by capital letters. So for example, capital B might represent the number of babies in a pregnancy. Is that a discrete or continuous random variable? Discrete, right? Because you can't have half a baby or a tenth of a baby. Everybody agree? Let's say capital M equals the mass of chips in a packet. Discrete or continuous? Continuous, right? Because those chips could weigh any amount as accurate as your scale could go. You can get as many decimals as you want out of that, right? Everybody agree? T is the time taken for a runner to complete a 100-meter dash. Discrete or continuous? So there's only finitely many times that a runner could run a 100-meter dash in? No, right? That's continuous, right? If your clock is accurate enough, you can get as many decimals as you want on that. Let's say X is the number of sixes obtained when you roll a die 3 separate times. That's discrete, right? What are the possibility or possible outcomes there? 1 6, 2 6, or 3 6s? Everybody agree? All right. We just did that. So let's start talking now about something called a probability distribution. Okay? So a probability distribution or a probability model, you can use those two terms interchangeably, is just a list of every possible value for a random variable, and then the probability that that specific outcome will occur. Oops. So just like in chapter 8, the probability distribution requires two parts. We have a sample space, that's all the possible outcomes, and then a probability for each of those possible outcomes. Is everybody okay with that idea? Now for a discrete situation, you can just make a list. Because you have finitely many outcomes, we can just kind of make a list, like with our rolling 2 dice example. If you have a continuous random variable, can you make a list? No, because you're going to have infinitely many outcomes. So we have to do something a little bit different there. We'll see what that looks like when the time comes. I don't think we quite get to it in this first section. So, as an example of a probability distribution, say that we roll 2 dice and want to find the sum of the resulting rolls. So our random variable, I'm going to call x, and that's going to equal the sum of the 2 dice. So far, so good. So, oops. So if I want my sample space, so I could get 2. There's one way I could get that. I could roll a 3. There's 2 ways I could get that. We can roll a 4. There's 3 ways to get the 4. I could roll a 5. There's 4 ways to get a 5. Everybody see what I'm doing here as I'm going? So this is our sample space. To calculate our probabilities, I'm going to take the number of times that dice can roll, that roll can occur. I'm going to add those all up. I get 36. So the probability of rolling a 2 is 1 out of 36. Rolling a 3 is 2 out of 36. Rolling a 4 is 3 out of 36. So that's the probability for each outcome. Does that feel okay on what I'm saying? So once you've identified the possible outcomes, that's your sample space. So our sample space was the outcomes 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I want to see how many times that outcome can occur. So I listed the way I can roll a 2, just getting a 1, then a 1. There's only one way that can happen. Then I want to list the number of ways I can get a 3. I could roll a 1, then a 2, or I could roll a 2, then a 1. So there's 2 ways that can happen. And I go on and so forth, and I want to count how many times each outcome can occur. Does that feel okay with everybody on what we did there? Because I need the number of times the outcome can occur to calculate the probabilities. So we just talked about this. Probability x equals 0. Oh, this is a different situation. I'm sorry. We're going to calculate the probability of x, which represents the number of 6s obtained when a dice is rolled 3 times. Okay, so let's think about the sample space. What are the possible values of x in this sample space? So x represents how many times we get a 6 if we roll a dice 3 times.
So when you say a 6, no 6, no 6.
Well, that's a way to get. That's the number of ways you can get, like 1 6, but that's just 1, right? So
1, 2, 3.
And 0, right? So there's 4 outcomes here. You get 0 6s, get 1 6, 2 6s, 3 6s. Now, getting 0 6s Lots of ways that can happen, right? No, just one way, right? Not a 6, not a 6, not a 6. Okay. How many ways? Well, depends on how you look at that, right? Because you could get like 1, 1, 1, 1, get 1, 2, 3. So like depending on what you mean by ways, but yes, if you think about it as just not 6, not 6, not 6, then it's just one way. How many ways can we get 1 6?
3 ways.
3 ways. You get it 6, not 6, not 6, not 6, 6, not 6, or not 6, not 6, 6, right? 2 6s, again, you can get that 3 ways. The not 6 could be first, could be second, could be third. And then 3 6s, there's only one way of that happening, right? It's just 6, 6, 6. Ooh, devil. Okay, so P of 0 would mean after 3 rolls, that's the probability of getting 0 6s. P of 2 would be after 3 rolls getting 2 6s. P of X would mean we're looking for all the possible outcomes and the associated probabilities, i.e., we're looking for the probability distribution. So let's build ourselves a probability model. So roll 1, we could get a 6 or not a 6. Everybody agree? Probability of getting a 6 is 1/6, and not a 6 is 5/6. Roll 2, we get not a 6 or a 6. After rolling a 6, and after rolling not a 6, again, we could get 6 or not a 6. And then for our third roll, we do the same thing. So this is a probability tree diagram that's going to help us come up with our probability distribution, right? So if I count at the end, I have 1, 2, 3, 4, 5, 6, 7, 8 possible outcomes, right? Everybody see that? So in my sample space, the number of times things can occur, there's 8 different ways that X can occur, right? So I see to get 3 6s, there's just one way of that happening, and the probability would be 1/6 times 1/6 times 1/6. The probability of getting 2 6s, I can get 6, 6, not 6. That's one way. 6, not 6, 6. That's 2 ways. Or I get not 6, 6, 6. That's a third way. So there's 3 ways that that can happen. They each have the probability of 5/6 times 1/6 times 1/6. But since there's 3 of them, we multiply that by 3 or add 3 of those together. Either way of thinking about it is okay. You guys kind of getting the idea? So this first line is 3 6s. This outcome is 2 6s. This outcome here is 2 6s. This outcome here is 1 6. This outcome here is 2 6s. This outcome here is 1 6. This outcome here is 1 6. And this outcome here is no 6s. And here's the associated probabilities. What should happen if I add up all these probabilities?
Equal 1.
It should equal 1, right? Can't be a probability distribution if all your outcome probabilities don't equal 1. Is everybody okay with how we kind of computed this probability distribution? Again, I like pictures. I like drawing a picture. I like being visual. I like having something to kind of look at and conceptualize in my head so it's not quite so abstract. Building a diagram like this for a problem is super duper helpful, right? Where we've now just like drawn out all the possible outcomes without having to think about what they are in our head. I've just drawn it like systematically what could happen as like a choice diagram. So these tree diagrams that we used last chapter, still quite helpful. Okay, so at the end, probability of getting a 0, there's just one way to do that. Probability of giving a 1, there was 3 ways to get that. The probability of getting a 2, there was 3 ways of getting that. And the probability of getting a 3, there's just 1 way to get that. So if I were to summarize my probability distribution, it would just look like this box. That would be all I would write down as a final answer. Now, I used all that other stuff along the way to make sure I had the right answer. Particularly since it's our first time doing it, I want it to be really super clear and like really write out everything that I did so you can see how we're getting these values. But that's the idea. Do you guys feel okay? And again, if I add up these 4 values, I get 1. I know it's hard to see that here because the denominators aren't common, but if I were to draw a this isn't the bar graph. This is the other one. What's histogram? Thank you. This is what it would look like. So the probability of getting a 1 is 5787. That's just 125 out of 216. And the probability of getting a 1 is 34.72. That's the 25 out of 72, et cetera, et cetera. Is everybody okay with the histogram that we drew? Particularly when we get to the continuous random variables, we're always going to be looking at a picture as opposed to doing what we just did because, well, there's infinitely many outcomes. You can't really draw a, you can't enumerate it out to get it. So we're always going to be looking at a graph. So if I think about these rectangles as an area, so the width of this rectangle is 1, and the height of this rectangle would be like 0.58 or 0.5787. If I look at this rectangle, again, its width would be 1, and its height would be 0.3472. If I look at this rectangle here, again, its width is 1, but its height would be 0.0694. This rectangle would be, the width would be 1, and its height would be 0.0046. If I calculated the area of each of these rectangles, that corresponds to the probability of getting a 0, probability of getting 1, probability of getting 2 6s, probability of getting 3 6s, and the sum of these areas is equal to 1, right? This will be the idea when we get to continuous random variables, is we're going to draw a picture, and then to calculate our probabilities, we're going to be looking at areas under the curve that we have. So we're going to be calculating areas. The calculator will be doing it for us, but that's really what's happening. Okay. Yeah, as we already said, that if I add up all these probabilities, I better get 1. So our basic rules for probability, still the same as from last chapter, right? That a probability is a number between 0 and 1. S is the sample space, so the probability of the sample space has to be 1. If we add up the probability of all the outcomes, we better get 1. In the case of equally likely outcomes, the probability of getting outcome A is just the number of ways that A can happen divided by the total number of possible outcomes. Our expectation, our expected value. So if we do n trials, that has a probability of A occurring as A. The expected number of times event A would happen would be the number of times we did the trial times the probability that that event happens, right? So just as a common sense, we flip a coin 100 times. We'd expect how many times to get heads? 50, right? 1/2 times 100. We roll a dice 6 times. The expected number of ones we'd roll would be 1, right? 6 rolls times 1/6. Everybody's okay with that? Okay. All right. So if we change this now to probability distributions, it's P of any x needs to be between 0 and 1. The sum of those probabilities has to equal 1. P of x is just the total number of ways that x can occur divided by the total number of outcomes. The expectation for x, the expected value of x, is just the sum of x times the probability that x occurs. And then the complement rule, that the complement of a is equal to 1 minus a. So the probability that x is not equal to x is 1 minus the probability that x equals x. So it's the same ideas. We've just changed the notation, because instead of dealing with like a single probability, we're looking at these probability distributions, right? So we can say this is now not true just for one outcome A, but for like any kind of outcome. All of these things still kind of hold. Everybody's cool? All right. So what we'll talk about now is something called a cumulative distribution function, also known as a CDF. And what this function does is it computes the probability that for a random variable x, the observed value is at most a certain amount. So that's a little wordy. Let's look at a specific example. So we say a cumulative distribution function is a total probability that some random variable x, the observed value is at most the indicated value of x. So suppose that x is a student's scale score on their IA. The CDF below shows the cumulative probability for each score from 0 to 7. So the probability that we got at least a 0 is like 1%. The probability you got at least a 1 is like 4%. At least a 2 is 12%. Notice I'm saying at least a 2, so that means you could get a 2, a 1, or a 0. Is everybody okay with that? So given that, what's the probability of getting exactly a 2? 12 minus 4. So 8%. Why don't I have to subtract the 1? Because the 1's already housed inside, right? Because it's accumulating as we go. Notice when we get to a 7, what's the probability there? 100%, because the probability of giving at least a 7, well, that's all of that means you got it, a 0, 1, 2, 3, 4, 5, 6, or 7. Am I saying at least? I mean at most, right?
Oh, yeah.
Sorry, that's the wrong verbiage. Excuse me. So notice that the function is not a probability function. Okay? But when we denote a CDF, we denote it as like an f of x, not a p of capital X, right? X is not a random variable here. The way to find our CDF is just to add up our various probabilities. So again, f of x, our cumulative probability distribution, is the probability that x is less than or equal to some value. So to do that, it would be like, if I did f of 5, that would mean that's equal to p of x is less than or equal to 5. So if it's a discrete distribution, it would be equal to p of 0 plus p of 1 plus p of 2 plus p of 3 plus p of 4 plus p of 5. That's what we mean by adding the various probabilities. Let's look at a specific example. Actually, let's relate this back to something we did in chapter 5, excuse me. So remember in chapter 5, we talked about cumulative frequencies and cumulative relative frequencies, right? So here, what this table indicates is the probability of a student scoring at most a 4 would be f of 4, which is 0.55, because that means you could score 4 or 3 or 2, 1 or 0, right? What's the probability of getting exactly a 4 have to be? 0.55 minus 0.31, so like 14%. Is this feeling okay? So what if we wanted to find the probability of just a single score? Like the probability of getting a 7 is we take the probability of getting at most a 7 minus strictly less than 7. So that's going to be 1 minus 0.92, so like 8%. And we can continue doing this for each possible outcome, right? What's the probability of getting a 6? 0.92 minus 0.77, right? What's the probability of getting a 5?
22.
0.77 minus 0.55. What's the probability of getting a 4? You mean 14? Oh, 24? It is 24. I screwed it up earlier, huh? Arithmetic is hard, guys.
Yeah.
Probability of getting a 3, 0.31 minus 0.12. Probability of getting a 2, 0.12 minus 0.4. Probability of getting a 1, 0.04 minus 0.01. Probability of getting a 0, well, that's just 0, right? Probably getting less than or equal to 0, when 0 is the lowest thing, it's just going to be the probability, same thing as probability of getting 0, right? Or you could take everything else and subtract it from 1, right? Either is okay. So right now, this would be our probability distribution. That's what we've just created, right? We've gone from a CDF, a cumulative probability distribution function, and converted it to a probability distribution. That's what we just did. How do I know that this is a probability distribution? I have to check two things. All the values between 0 and 1 are all the probabilities between 0 and 1. And do all the probabilities add up to be 1? Everybody's cool? So we just checked those two things and we know we have a probability distribution. Do we feel okay doing that? Again, the vocabulary is like the hardest part, right? So we just have to get comfortable there, but the actual arithmetic that we're doing, just like adding and subtracting things here, it's not super duper difficult. And like counting the number of times something can occur, it's usually pretty straightforward. Okay, let's look at a specific example. So when people create codes for their cell phones, the first digits follow the probability shown in the table below. So, 0.009 is the probability the first digit of your passcode is a 0, etc. What is the probability you pick a first digit that is more than 5? So what are the first digits that are more than 5? 6, 7, 8, 9. So to find the probability you got a 6, a 7, an 8, or a 9, we add up those four probabilities, right? So the probability that x is greater than 5 is just the probability that it's 6, plus the probability it's 7, plus the probability it's 8, plus the probability it's 9. If I add those all up, I get 0.221. Does that feel okay? Not super difficult. show a probability histogram for the diagram. So what am I going to do here? I draw basically the bar graph where the bars touch, right? The x-axis should be a bar for x equals 0, x equals 1, x equals 2, x equals 3, x equals 4, all the way up to x equals 9. And the height of the bar is just the probability. So I used Excel to generate this thing because if neatness counts, I'm not doing it by hand because you've seen my penmanship and it's, while it's not like brutal, it ain't great. I've seen a lot of your penmanship and we could say the same thing about a lot of ours, right? You know who I'm talking about. Everybody's okay on the histogram, right? It's pretty easy. All right, so let's talk about expectation now. Remember, this was one of the things that was properties of probability distributions. So again, if we think of just common sense, expectation is the expected outcome. So again, the analogy I always go back to thinking about, if I flip a coin 100 times, the expected number of heads I get is 50. So here's our probability distribution. You might recognize this as our rolling 3 die and getting a 6. So the expectation is the sum of the outcome times the probability for that outcome. So if I did this for the entire probability distribution, I get 1/2. So if I roll 3 dice and I count the number of 6s, that is the average number of 6s I would have expected to get. 1/2 of a 6. Everybody's okay with that? Because the probability of getting 0 6s is this. So 0 times that gives me the expected number of zeros I would get. 1 times this gives me the expected number of 1 6 rolls I would get. This is the expected number of 2 6 rolls I would get, or the number of times I would get 2 6s. So if I add those up, this is like the number of 6s, number of 6s, number of 6s, number of 6s. I add these all up and I end up with 1/2 a 6. Everybody's okay with this idea? Okay. So let's look at another example. So again, we have some random variable x and a probability distribution. It asks us to find the value of c. How could I do that? What's that?
1 minus everything else.
1 minus everything else. You're close. It's not 5. What do you know about a probability distribution? What do the probabilities have to add up to be? 1.
So 1 equals.
So I just add them up and set it equal to 1 and solve for C. Everybody's okay? Isaac, you were close. Used the wrong property of probability distributions, but you're right to think about your properties of probability distributions. Everybody's okay with that idea? Once you've seen it once, it's like, okay, got it. Okay. Find the probability that x is greater than or equal to 4.
Oh, plus 3.
Yeah, so I have probability that x equals 4 plus the probability x equals 5. Or we could do 1 minus the probability that x is less than or equal to 3. Either is okay. This is less adding, so that's the way we did it. Again, c is 120, or 1 over 20, so I have 3 over 20 plus 1 over 20, so 4 over 20.
Then 4c.
Sure. Absolutely. You could have added the 2 and then plugged this 1 over 20 in. That's fine. Okay. Let's do the expectation for x. So I'm going to do 1 times 7 over 20 plus 2 times 5 over 20 plus 3 times 4 over 20 plus 4 times 3 over 20 plus 5 times 1 over 20. Is everybody okay with that? And I get 2.3. So I'd expect this experiment, the average value, if I did this like whatever times, like 100 times, 2.3, if I added up all the outcomes, 2.3 would be the average, right? So I get a 1, 2, 3, 4, or 5. Those are the outcomes. I do that 100 times, I add them up. And take the average of all those outcomes, I'd expect 2.3 to be that number. Does that make sense as to what this expectation is saying?
This doesn't give how many times. So
that's not the number of times, that's the outcome. So we have 5 outcomes, 1, 2, 3, or 5, 1, 2, 3, 4, or 5, right? Say we did this 10 times. We got like a 1 and a 3 and then a 2 and a 5 and a 1 and a 2 and a 1 and if I add up those and divide it by 10, I'd expect it to be around 2.3. So the 1 plus 2 plus 5 plus 1, whatever. If I added up those outcomes, and took the average of them, I'd expect it to be around 2.3. Is that okay? It's kind of like the average value for this probability distribution. Okay. So let's talk about variance and standard deviation. Remember from previous, standard deviation measures the average distance of our observation from the mean. We calculate it by finding the average of the squared distances and then taking the square root. And the average of the squared distances we called variance, right? So like if we go back to, I don't remember what chapter this was, like 6 or something. The variance was this, right? These are the average of the squared distances. So the mean is x bar, so the distance from the first observation to the mean is that, and then we squared it. And we did that for every observation, and then we divided it by the number of observations, right? So that's, or we write our formula this way, means the same thing. And the standard deviation is just then the square root of that variance, right? So what does this mean in a probability distribution sense? So to find the mean in a probability distribution, we do we add up from 1 to k, and that's, what is f in here? Oh, there we go. Okay. I was like, what is this going on? Okay, so mean is just expectation. That's what I was expecting. It's like, what is this doing here? So mean, if I want the mean value in a probability distribution, I'm just calculating expectation. So the same way we just did. If I want the variance, that's going to be the sum of each outcome minus the mean squared times the probability for that outcome. And the variance then is, or the standard deviation then is just still the square root of that variance. Are we out of time here? What's the 9:15? Remind me where we left off on slide 24, and we'll pick this up next time. I think they're already in the thing. Let me check real quick. What's up? No, you can keep them. Oh, they're not. I'll get them in there today then, Lexi. Yep.